All right, we're going to review using the color sensor and on your microcontroller. And before we do that, we're going to kind of understand how it communicates with our Pico. And it's using something called I2c or I2c, which is Integrated Circuit Protocol, and that's why it's called I2c. And this is basically a way that the microcontroller communicates with the Pico. And this is basically that communication protocol. And this is a standardized protocol. And the reason we have standardized protocols is so that we can use them among lots of different devices. Okay, and if we look up, I2c protocol, we could see where it came from. And so it was invented by Philips Semiconductors, now called NXP Semiconductor, in 1980. Okay, and so this is used generally for like kind of lower speed data, but it's useful. If you want to connect like a whole bunch of sensors and just use two wires, you connect all these peripherals using the same two wires. So you have a data one and a clock one. And you're able to basically communicate with a whole bunch of devices that have different addresses on that same bus, okay? And there's a whole bunch of other types of communication. So there's a kind of communication called serial communication, where we use something called a UART. And this is actually how some microcontrollers will communicate with a computer over the USB port. They'll have what's called a USB to serial converter. With the Pico, it's got something else, I think. But so this is a pretty standard form, and so you can really only communicate with, this is two-way communication between a pair of devices using serial. We have another kind called SPI, or Serial Peripheral Interface, and this is for, this can be a lot faster. It's used for like displays. It's used for, for like flash memory and stuff like that. And so this is a faster form of communication. But if you don't need super high speed and you want to connect to a bunch of different sensors, then I2c is a great way to go. And you can see, like, if you're using SPI, you need a lot more connections. You have basically you differentiate between devices using SPI using a chip select. And yeah, I mean, it's just a different method, so it's faster, higher tech. I2c is a little bit simpler. It does have its issues where things are configured wrong and won't work, but we use this I2c, and it communicates with a clock signal between 100,000, 400. You can probably go lower than that too, but 400,000 hertz is usually kind of the max there. And I wonder if they're going to show us what it looks like. Oh my god, here we go. So if you were to connect a I2c bus to an oscilloscope, you're going to see two things. So when there's communication happening, you're going to see this clock line toggling, and then in bursts basically, and along with that you're going to have some data, and you can have address, so where it's telling which device it's talking to, it's got the actual data. And so we don't, for our purposes here, you don't need to know a ton about it. If you were going to get into, hardware design and firmware design, this is something you'd want to dig deeper into probably. But in the meantime, we just need to kind of know what it's called. We don't necessarily need to know all the specifics of it. But so for our purposes, we're going to be using this, and let me pull up the sensor. And so we're going to be using I2c to communicate with this sensor. And so there's a couple things here. You can see the SDA and the SCL pins. This is the serial clock and the serial data. And so for the Raspberry Pi, we have several different pins that we can connect that to. Depending on the microcontroller that you're using, some of them have dedicated I2c pins that you have to use for I2c. And then there's some that have like several options, and there's some that have like fast options versus slow options. If it's got like a hardware component that controls it, or it's controlled in software. So anyway, the point being is this is what we're using here, those SDA and SCL pins. We've got ground connection. We have V in here that we're connecting at 3.3 volt. it's going to run through a sorry, my brain right now. A regulator, which I'm not sure exactly how this works, but because we can also power direct 3.3 and 3.3 volts, but we're running through this one. We also have this interrupt pin right here, which we can use to trigger a reading, you know, if something changes. But since we're not like trying to do like a low power thing or something, or like super fast stuff, you know, we're not worried about this. And then we also have this LED one where we can actually turn this LED off if we wanted to in between readings. And we don't really need to worry about that either. And so those are the pins that we're using. And we'll get into now a couple of these scripts here. So we have this run cal one, which is basically going to calibrate it and give us our values. And so when we do the calibration, the way that we do this is we want to be in a scenario where we have very low ambient light and we have like a black background, and then we put like a white object over it. So kind of like a matte white plastic object is what I've been using. Getting a good at calibration is essential for getting color readings. So I'm using this random plastic thing that I found, and the way that we do it is we're going to be connected. We've got this run cal script, and basically you're going to hold that thing over the sensor and you're going to click this, and this is going to, oops, didn't like that, line 12, this thing got broken, there we go, line 15, this got broken too, I wonder what happened there, okay. Okay, so I'm going to run it, and it's done this gain calibration for me. I'm going to reset this, okay, I'm going to run it again, so it runs, takes a minute, and then it's going to spit out a value here, okay? And so what it's doing is, it's calculating this gain here, and this is kind of like, there's two different gain levels. One is for computing and normalizing the RGB values, and one is an actual like sensor like calibration setting. And so basically what we want to do from here is we want to take these 4 lines, and we're going to copy them, and we're going to paste them into our read color script. Okay? And, you know, we would maybe want to move the time here, like that. And then, you know, maybe we want to change the formatting. But essentially, you want to put it here. So we want to import this gain 16x here, like that. And we're going to set our sensor gain to be 16x. And then the RGB gains, we're going to copy this one right here into here. Okay? Now I'm not going to use these values because this calibration happened with the kind of like ambient light and stuff, which is not what I want. And so I'm going to actually revert to what I had before. So when you do that calibration, you want to make sure that it's in a, basically that there's kind of a, you know, we're going to build like a sensing chamber. So using your sensing chamber, you have a dark background, you have some like a white object in front of it, etc. Okay? And then once we've done that, we've input our calibration here, we're going to run it, and then you can see it's just going to sample for a period of time. Okay? Now I'm going to copy this over into a spreadsheet real quick. I'm going to go copy, I'll click over to here, and I'm going to go, let's just go paste, Control V, and then we're going to go split text to columns. Okay? And so we have a bunch of values here. And so because my calibration is bad, these RGB values are kind of all over the place. I believe it should be 8-bit based on the normalization, but I'm not sure. But like when we're sampling, you know, look at the bottom here. You can see this changes when they have like a white object over it. Or if we put something that's kind of yellowish, we're getting a different reading. This thing's orangish. Okay. And one of the things that you're going to want to start doing is basically you'll run this script a bunch of times once it's calibrated with different colors in there. So you might grab some data. Let's say we put a blue M&M in there, and this was the data that we got. And then we're going to put a green one in there, and we're going to put our data right here. And then from there, we can kind of compare each of those data sets and look for things that stand out. And so I'll point out a couple of these things right now. The C value is called a clear measurement. And basically it's measuring the amount of light that the sensor is reading. And this is one of the reasons why we want that really dark background, because that dark background is going to absorb the light. And so our C value will be very low when there's no M&Ms present. And this can also be, you'll see that this changes based on the color a little bit too. But this can also be used to detect, for example, if there's an object there. Once you have a good calibration, you might see that this C value jumps over, a certain level when it's calibrated. And then we have these three values, R, G, and B, which is red, green, and blue, which is the three colors of light that our eyes see. And so our eyes have color sensors in them that are basically detecting red, green, and blue. And so like when we see something that's yellow, we're getting, red and green triggered at the same time, and it registers as yellow. And so you'll see like, with the yellowish colors that these two kind of spike a little bit. You'll see with the blue one that this one will spike, with the green one this one will spike. And then the thing that's challenging here is that the brown and the red and the orange and the yellow are all going to be very similar with their RGB values, especially the R value. And so what's helpful is we have this separate color space called HSV. And what you can do is you could think of like RGB as a set of 3D coordinates. So if we think about, if we've done some math classes or physics classes where we're plotting things in 3 dimensions, this is like an X, Y, and Z. And you could think of HSV as a separate coordinate type. And so if you've ever learned about, say, polar coordinates, you can convert from these 3D Cartesian coordinates into polar coordinates, and you don't lose any information. It's just a different way of interpreting the data, and it can give you different perspective on things. And so we have the same thing here, where RGB is a type of color space. Okay, where we have basically, kind of 3 values that we're merging together, and those combinations of values are going to give us our colors. And if we look at RGB color picker, you can see that this is RGB. No, this one's not RGB. Let's see. I want just RGB. Let's see. Here we go. This is an RGB color picker. You can see that using this, getting orange and brown, like this is kind of an orange and a yellow right here. They're not that far away, depending on our red color. And then brown is basically just like less of all of them, And so it can be tricky to distinguish brown and yellow and orange just because it's changes on this this red and green axis, and it's hard to distinguish. And so what can be useful is converting to that other color space called HSV. And this is a different way of interpreting it: hue, saturation, and value. And what this does, it's got this kind of 360-degree color interpretation. And so this can be helpful for distinguishing between yellows and oranges and reds with our hue value, which is the H. And so this H value we'll see some change when we look at the oranges and the reds and the yellows. And so let's look up a HSV color picker. There. Okay. And so looking at HSV, basically this bar is HSV, and so you can see that as we change our H value, right? So as we change this, you can see it's changing the H value. So you have a different H value for yellow, for orange, for red, and then when you look at orange, that's going to be tricky to distinguish from brown a little bit. And then we also can look at, then some of the other values. But so HSV will be useful. That H value is going to be useful when we want to distinguish between the browns and the oranges and the yellows and the reds. And then the C value as well will play a role there. So like the C value for brown is going to be lower than the C value for orange because it's going to reflect less light. And so the values that we're getting here from the script probably aren't going to be true RGB and HSV values, but they're going to be good enough for what we're doing to sort these M&Ms. Because I don't think they're normalized right, but that's okay. And so we'll mess around with this, and then eventually what we're going to do is we're going to build this into a function that we're going to use to sort or determine the color. And so we'll first determine if there's an M&M there or not using that C threshold. Then we'll sort between the R, G, and B. So we'll grab out the green and the blues, and then with the remaining we'll look at the R and the H and the C to determine yellow and orange and brown and red. Okay, and so that's enough to get us started. I've got these scripts that I gave you here, this run cal script, which is going to be useful, and then this script right here, which will be useful as well. Okay. Oh, let's see, go back to it. All right, and so that should hopefully be enough to get you started. And yeah, I'm looking forward to kind of seeing us get our calibration right and starting to be able to sort colors.